All right, guys, so we're back going over Unit 1 and we're starting Part 3. All right, so now 1-5 is all about IMFs. So remember intermolecular forces, intermolecular interactions, that kind of thing. So remember hydrogen bond, you got to have Fon, right? Dipole dipole is just as, so hydrogen bonding is just a special type of dipole dipole. I know that's the positive dipole, that's the negative dipole of that molecule. So that interaction right there is called a hydrogen bond. Okay, but over here we don't have one of our special Fon bonds, so this dipole dipole interaction is a dipole dipole interaction. Remember, London dispersion is just a spontaneous or instantaneous or non-permanent dipole dipole interaction, right? So at any given point in time, right here, a methane molecule, more electrons could be over here, and the same thing happens over here. All right, so like, you know, all of a sudden there's more electrons on this side of the electron cloud, more electrons on this side, so this side's positive, that side's negative, and then you get that non-permanent dipole-dipole interaction. We call it London dispersion. So remember, the bigger the cloud, the more likely that you have an uneven distribution of the electrons within the cloud. So the more London dispersion, or the stronger the London dispersion is, or the more polarizable it is. That's the way to talk about what London dispersion is. All right. Then you have ion-ion interactions. It's just an ionic bond, right? Then you could have ion dipole, right? So like think of an ionic compound, salt dissolving in water. The water has a dipole. The ion has an ion. The interaction between the negative dipole of a polar solvent and the positive ion is an ion dipole. You could also have the positive dipole of water interacting with the negative ion, right? So you could have this side of the water molecule interacting with that ion. That would be ion dipole, all right? And then we have this thing called dipole-induced dipole. So think about like a polar molecule has a permanent dipole, and then a nonpolar molecule, the electron cloud of this molecule might be affected by this dipole. And so this positive dipole could be pulling on the electrons within this cloud and pull the electrons over here, and that's called an induced dipole. It's a dipole that's induced by this dipole. So it's a non-permanent dipole, induced dipole, and it's been induced by a permanent dipole. So this is called dipole-induced dipole. So like, this is what's going on in like carbonated water, right? CO2 is dissolved in the water, it's mixed with the water. Well, what's holding it together? These types of interactions, dipole-induced dipoles. Now, they're not that strong, and that's why when you open up your can of soda, the CO2 starts to escape right away because it's not very water soluble, but, right? Okay. And so, intermolecular forces correspond to chromatography. Remember, what chromatography is a way to separate mixtures based on how fast they move through a medium. And so basically the speed in which they move through the medium is going to depend on how much they interact with the medium. If they don't interact with the medium at all, they're going to move fast through the medium. If they're interacting with the medium a lot, then they're going to move slow through the medium. So here we have a piece of paper, and so the paper is the medium that this this mixture of ink is going to move through. Okay, and the mixture of ink has two components. It has component B and component A. All right. Well, here we're told the paper is polar. So if the paper is polar, the less polar thing is going to move the furthest because nonpolar doesn't interact with polar well. And the thing that moves the shortest through the medium, or not as fast through the medium, is going to be more polar. So, but then if we change the paper to nonpolar, that means the nonpolar thing is going to not move as fast, and the more polar thing is going to move faster. So based on this, we know that B must be more polar than A, or maybe B is polar and A is nonpolar, right? Okay. So again, organic shows up, but it's really just about IMF. So like here we got butane, we got propanal aldehyde, and we got propanol alcohol. You don't have to know that this is propanol. You don't have to know that this is propanol. You don't have to know that this is an alcohol group. You don't have to know that this is, well, maybe butane. You know, we did go over that kind of nomenclature back in Chemistry 1. But the main thing is hydrocarbons, nonpolar, so only London dispersion. Okay, this is polar. When you have an organic compound with a functional group, you're polar. But since it doesn't have a Fon bond, it has dipole-dipole interactions. And remember, everything has London dispersion. And then alcohol, it's polar, but it has a Fon bond, so this has hydrogen bonding and London dispersion. Okay, so remember, everything has London dispersion. Okay, normally we just focus on the stronger of all the IMFs that it has, but sometimes you have to list them all. Okay, so what do we know? We know that, you know, of these three molecules, we would expect this one to have the highest boiling point because it has the strongest IMFs, and this one had the lowest boiling point, and then we would expect this also to be the most water soluble, and this would be the least water soluble, because remember the rules, like dissolves like intermolecular forces mix with like intermolecular forces. So you can't just say like dissolves like if they're asking like why is this one less soluble, or maybe why is this one more soluble in water. It's because you would say, you can say like dissolves like, but then you have to explain why they're alike. And you would say, well, propanol has this, is polar, and because it has this bond, it has hydrogen bonding. Water's polar with hydrogen bonding, so therefore they're going to mix well together. You know, this would be soluble in something like benzene, because benzene's nonpolar, and you know this is nonpolar, right? Something like that. Okay. Okay, and then 1-6. So the things you want to remember about ionic compounds is they have high melting points. Metals tend to have high melting points, and big covalent compounds can have some high melting points. Like sugar has a decently high melting point, like compared to like something like water. But the differences between them, ionic structures can't conduct electricity in the solid state, but will conduct electricity when the ions can move. So if it's melted or if it's dissolved in water where the ions can move, they can conduct electricity. Metals can conduct electricity in the solid state, and then covalent compounds aren't really going to conduct electricity at all, unless it's like, you know, a carboxylic acid, which would be a weak electrolyte when dissolved in water, because it would produce ions because it's an acid. Okay, but you know, like you've seen questions on multiple choice maybe where they say this substance has a pretty high melting point. It didn't conduct electricity as a solid, but did conduct when we dissolved it in water. That would tell you it's ionic, right? If it had a high melting point and it did conduct electricity as a solid, then you know it's metallic, right? If it didn't conduct electricity at all, then you probably think covalent, right? So that's, you know, things to remember. So remember what you know, a simplistic picture of an ionic compound structure looks like: positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, just repeating units, right? Now, sometimes they might be bigger / smaller spheres, and you'd have to be able to use, you know, your ionic radius knowledge to know, you know, is the negative ion have the larger radius, or does the positive ion have a larger radius? So like if it was sodium chloride, the sodium has the smaller radius, the chloride has the bigger radius. But if it was like cesium fluoride, fluoride would have the smaller radius and cesium would have the larger radius. So you want to watch out for that. Also remember, a cleavage point in an ionic structure is when you've pushed, like maybe you pushed down here and you pushed up here, and you get a negative next to a negative and a positive next to a positive, and that would naturally separate because those ions would repel each other. So that's kind of a breakage point or a cleavage point in ionic structure. Okay. So a metal kind of looks similar. You're going to have a bunch of positive spheres next to each other, but notice it's not positive, negative, positive. Now you might have a very small negative particle written, and that's going to represent electrons. But notice they're not going to be kind of in a repeating structured form, right? The electrons are just going to be kind of spread, you know, randomly within the structure, and that's trying to show you that metals have a sea of delocalized electrons that can go from one nucleus to another nucleus to another nucleus to another nucleus, and that's why metals are good conductors of electricity. Okay. Then you have like things like alloys. And for alloys, you want to be able to distinguish between interstitial versus substitutional. So when you have things that are similar in size, right, they're just going to be like, so if this, let's say the colored in ones are copper and the other ones are zinc. If this were all zinc, then they should all be, not colored in. If it was all copper, it would all be colored in. But an alloy is a mixture of two different solids here. So in substitutional is, okay, I substitute a zinc with a copper, right? Substitutional. When they're same size, they're similar in size. They don't have to be exactly the same size, but similar in size, you're going to have substitutional alloys. And then like steel is like and I shouldn't have said iron here. I should have said steel. Steel is an alloy of iron and carbon. Right? Iron is a lot bigger than carbon, so then we get interstitial. So you're not going to replace iron with carbon, but within the small little holes that are made by these atoms lining up next to each other, that's where you put the carbon atoms, and that's called interstitial. So when you have a big atom and a small atom, you're going to get an interstitial alloy. When you have similar sized solids, you're going to get a substitutional alloy. Okay. And then the last thing, recognize these as network covalent. If a covalent compound has an unexpectedly high melting point, it's a network covalent solid. Okay, these are the most common ones, but there's others, and so just be ready for that. It's like, why does this compound have an unexpectedly high melting point? It's like, oh, it's a network covalent. Okay. All right. All right, so I don't know if you can see me or if you see a blank screen because my camera is weird. I'm seeing a blank screen. It's supposed to be me on camera. All right. So I'll take myself off just in case. But hey, that's Unit 1. Those are kind of the important things to go back and just remember. They'll help you save time on the exam. And a lot of times that's half the battle, man, is the test taking skills. Not taking too much time on one question. Knowing when to cut and run. Understand that most years an 80% is a 5. Okay? So, yeah, it would be awesome if you were the first West Springfield High School student to ever get a perfect score on the AP exam. That would be fantastic. But odds are you're going to make a mistake here or there. So, know that as you're taking the test, if you start struggling on a question, but you find yourself, man, I've spent 5 minutes on this multiple choice question. That's too much time to spend on a multiple choice question. Cut and run, right? If there's time after you complete the multiple choice section and you still have time left, then go back and start thinking about it a little bit more, right? But make your best guess, put it down on the Scantron just in case you run out of time and you don't have time to go back and make a guess later. And never leave anything blank, right? Make a guess and try to get as many points as possible, right? But it's not necessarily getting 100%, right? If I get an 80% and I get a 5 and you get 100% and you get a 5, guess what? We both get a 5. No one's going to care that I got an 80% 5. If you get 100% 5, then I'm taking you out to Ruth's Chris, and it's on me. All right. So, if you get 100%, that'd be great. All right. But odds are it's not going to happen. Right. Right. It happens maybe one student a year out of the world gets 100%, and there's some genius kid who's like a 10-year-old prodigy. It's like, okay, great. All right. You're not that person. So maybe you get a 95%. That's a 5, right? In some years, I've seen it as low as a 75% is a 5. So, understand you're not trying to be perfect here. Part of the test is going fast. Part of the test is test-taking strategies. It's a big part of the test. It's not like chemistry is about 60%, so your chemistry knowledge will get you 60%. Your chemistry knowledge could get you up to maybe a 3 or a 4. And then test taking skills is what's going to get you from a 3 to a 4 or a 4 to a 5. Test taking skills. All right. Anyway, I'll stop talking. Have a good one.